Okay, so first of all, we're talking about the first question, which is what do you need to do to a spring to give it energy? And we're going to be working with springs today. So, any thoughts on what I need to do? You've got like all different types of springs. What do I need to do, Vincent, to give a spring energy?
Well, you can compress it or stretch it.
Compress or stretch. All right.
Or you can coil it as well.
Or you can twist it even more. If I were to twist it, hopefully I don't ruin this. If I twist it more, it will bounce back. And that's also any sort of bounce back is also an elastic energy. Good. All right. Let's talk about the different parts of a spring that make its energy different. So, Alec.
Like how much strength it takes to stretch it.
So we've got spring force. The strength it takes to stretch it is going to be equal and opposite, right, to the spring force itself. So I'm just going to call it spring force. And that's something that we can measure. So I'm going to include it on both sides. Anything else that we can observe or test from different springs? If you look at the picture, we provided the picture for a reason because you actually can observe the differences. Vincent?
I mean, you can also observe when it, I guess, collapses back together.
Observe. Are you talking about like the stretch, the distance in which it's
So once you stretch it and then let go of one end.
the rate of compression?
Rate of compression.
Rate of compression. So this is like a time value, maybe? So that's measurable. I'm going to call Alec, but I want some new volunteers too. Ah! Okay, so Alec, what else?
Whether it's like one of the coiled long ones or if it's like the spiral flat.
Coiled long ones. What do you mean?
Just like the shape of it.
Like if the coils are
you
spread
string
out?
that you pull this way or one that is flat where you like twist in the middle. Like in this picture they have this.
Oh, like these? Versus so the construction,
It's just like the shape of it.
the shape of it. Shape or how it's constructed. Anything else? Someone new? There's a lot of obvious ones. Sid? Thickness, good. Did you have a different one, Josh? Material, definitely. Anything else? Alex?
Just like size.
Size.
That's the same thing as thickness.
So you can have really, really big ones. Someone was saying you can have like the big ones you have in your car versus the little ones you have in your watch, right? So the size is important. How about we go into the things that you can measure from this or observe? Because we're going to do a lab today. So we're going to definitely have to collect data. What type of data besides the spring force, the rate of compression in the context of the time it compresses or stretches? Any other measurable things that we could potentially gather when we're doing a lab with springs? What do you think? What other measurements can I gather here? Anyone besides Alec? I want you volunteers. Something obvious.
How far you can stretch it?
How far you can stretch it. So, stretch distance. Anything else? Did you have something different than that, Chanel? What? Flexibility. That could be something in quality. Hard to measure, though I'm sure you can measure it in some sense. But these are the main things that I was looking for. What we're going to focus on in our lab, though, is the spring force. RING. I feel like. Okay, the spring force is going to be in newtons. The stretch distance, we call this delta x because it's a change. Anytime you have delta, it means change in position. And if I'm stretching my spring, I'm going to start at one position and increase it to another. So delta x is our distance, and that is going to be in meters. These are small springs. A meter is this long. So you're going to have to convert your centimeter value when you measure this to meters. Question out.
Just like stretch as long as the metal. Just like
So-
fully unstretch it and then break it.
Yeah.
where you-
So don't overstretch these. Look what happened. When my student overstretched it, it didn't bounce back. If you do this, I'm not going to be happy. And you don't want to see me unhappy. So I want you to make sure that these springs are fun. But if you play around with them and you overstretch them, I'm going to charge you $100 to buy me another set of these springs. Deal? Okay. I know you guys are good kids. I'm not going to. These ones are actually pretty expensive. I don't know exactly how much they cost, but I'm charging $100 anyway. Okay, so let's go ahead and look at our lab. Can you don't agree? Okay, so your lab worksheet is gray. We're only doing the first page. In the first page, it's going to have you gather data. So if you want, you need to determine the spring stretch. If you want, it has to be the distance from the string at rest to the string that is the spring when it's stretched. When you do that, though, you also need to find the force. So you're going to grab one of these, not this one, because this one doesn't have. You're going to grab one of these force sensors with a hook. You have to make sure it's calibrated, and then you're going to have one student hold it still on one end while the other student pulls it 1 centimeter. Check the force. 2 centimeters. Check the force, etc., etc. So I made this easier for you guys in my last class because I set it up a little bit later. But in your lab, on your Canvas, you are going to see in the agenda, this is for my tech people. If you don't know, if you're tech, my tech is yellow. So if you're yellow, I want you paying attention closely. For the tech and materials managers is never a good thing, right? Okay, shh. Tech people, it's not going to be hard, promise. You want to log into your Canvas because I have a link of the Pasco setup. We're not doing any graphing. All we're doing is collecting the force. So once you get to this link, you're going to download the Pasco Capstone application. You're going to open it up. And once it opens, let me move it over so you can see what it looks like. Once it opens, you should have just the digits in newtons. Now, it should start at 0. If it doesn't start at 0, you have to press 0 on your force gauge to calibrate. But press record first with no force on your force sensor. If it doesn't say 0, calibrate it, and then you can start measuring the forces. Okay? This is going to tell you forces in the negative direction. Keep all the forces positive, and then we'll talk about what the negative stands for later. Questions? Pretty easy. Everything from this lab is for you to calculate, to collect data, graph your data by hand, draw a line of best fit. So remember your line of best fit. If you're doing it by hand, you want to make sure that you have a few dots on top and a few dots on the bottom. Maybe a few that actually hit your line, but most of them should be evenly above and below. Now, if you look at your graph, there's this little dot right here. It's not a dot, so don't assume that your line should go through 0, 0. It's a 0 for the x-axis. This is your delta x, and it goes 0, 0, 1, 0, 0, 2. But a lot of my previous students had all their points kind of up here, but then they saw this 0 down here, and they thought, oh, that's got to be part of the line, so I'm going to try to draw a line of best fit connecting them. No, this is not a dot. It's just a 0 that got printed weird, and it's on the graph. Okay? Don't make the same mistake as my previous students. All right, let me have you get in your group. Materials managers, that's my pinks. I want you to grab a laptop, a spring. I've got all different colored springs. Everyone should be doing a different color. You're also going to need a ruler. Yes, grab one spring. Yeah.
It's only me and Alex today because we don't have Jack or Maddie.
Let me go ahead and see what how the groups are distributed, and I'll move some students in your group if I have another. Vincent?
Yes.
No thanks. Oh my goodness, that's what my son would be doing right now. Okay, so Mason, you guys have two? Who do you have? Are you the same number? Oh, so you have three. Oh, it's you and Josh, right? Okay. Anything else? Yes. Yeah, let me make sure. I don't have
Where do we get the spring? Bro, are you blind? It's right there. I don't see where
Yeah.
it's right to the left of the room. Okay, grab
Josh usually works with any group of three. If you
Josh.
Oh my god, it's so
Do we download that thing from Canvas?
Yes.
I'm sorry. I'm so sorry. I feel horrible.
Sure. Sam. Yeah. What color do you want? Yellow? Blue. Yeah, red.
Yeah, this is not working.
The horse sensor?
Not the first one, it's just
Is this music gonna distract you? Is this music doing turn this off? I was like, I'm just not.
Oh, I see.
Yeah, I guess we have
Okay.
Yeah, so we just do 1/6.
Sam, pull up. Bring the 15. Pull up. 3.
Yeah, we wrote it in our.
Thank you, Bubby.
What a change. How did Bobby really be called up?
What was the one
Pretty predictable. Yeah, it's just green. That was but it was
No, nobody has. It's kind of weird. Wait a minute.
Y-intercept doesn't matter. Y-intercept
Convert your centimeters to meters. How do you do that? Divide by 100. Divide by 100. Something's wrong with the.
Sarah who?
I'm not sure why. Alright, as you're working on this, if you get your mathematical model, you're going to do your 5% rule and you're going to write it up on the board based on the color of your screen. You didn't hear that.
Is the constant, what is it, 0.3?
So you need to convert. Your
0.03?
So I just removed that sign. If you convert your, so you divide it, yeah, so you want to divide it, this digit, whatever your height, divided by this, and you should get a bigger number. So when you look at the calculator,
Well, it starts there. You get that note. Whoa, that's how long are you?
What happened to that?
Oh, sorry, I don't know. I stopped well, it's like, I don't know. It's kind of weird. It's like I felt like. And I was like moving houses and shit. It was like really it keeps like it's like not feel like making that much of
When you take your flow, do you use the data points in your table, or do you use points from your line on your graph? Always use your line of best fit. Don't use your data table points unless they actually perfectly hit your line of best fit. Okay? 300 is too high.
I don't know what I'm doing. Right? So it increases by its point rate, right? That's the difference. And then it's divided by 0.1.
0.3 divided by 0.01.
That's why.
That's why. That
You say she walked into my class one day. Straight class. In my class. I love him. He's so nice. He was singing a song in class. I named Caleb. And he was walking. And then he was singing. And he was like, why do you seem so melancholy? And he's like, I don't know. He's like, I'll love it. But he like told me it's he's such a 0.5. Whereas he like say something like I want to laugh. He just talks about like I don't know.
I know a lot of you are already coming up with your slope and your y-intercept.
Yeah.
I want your facilitator to write that mathematical model on the board for me. Your facilitator is the green. My green folks. Once you get your math model, put it up on the board.
Mathematical model. Yeah, what's the slope? The slope is 30.
I didn't hear about that. Were you like talking about it? No, he just like Aiden. Well, I mean, you're like such a person. So.
The definition of your screen constant is at the very top of your paper. It is a new vocabulary word for this unit, screen constant. Read it. Also, if you get to 4, 5, and 6, I want you to give number 4 your most educated guess. Once everyone puts their mathematical model up here, we'll analyze what number 5 is going to be, and then we're going to do the annotations as a class. So just do 1 through 4 for now. Is what?
4, but slow.
4?
Yeah.
Oh, yeah.
Yes. Good. Yep. And let me have.
Why do we have 30?
That's your slope. But I want you to put it up there because the difference is you're gonna get this.
Is it okay if I do that next class and back?
Oh, no worries.
There's like no, it's just like, do it when we don't have it. I just did one of the bachelor's my later. Don't worry about me standing up for 5 hours with a
You're still working at the restaurant?
Yeah, how's it going? It's going good. And I'm working
You use the same video.
So my friends did that Wednesday, so I had to understand. There were 2 middle schoolers on the roof throwing eggs, Mars, and so I was like, the second I walked out and I screamed like bloody murder. I was so mad. And then I worked in the car. But I have work today and tomorrow. I just work for myself.
I love it. I love that about you, honestly.
Tomorrow, I'm going to by myself for 5 hours. And I have the night shift. So it's 4 to when we close, which is like the busiest time.
Yeah. Yeah.
So I'm very scared about that. I asked one of my friends.
You're hosting.
Yeah. I asked one of my friends. She was the one that I called her. But she just told me she's getting under the weather. I'm like, oh, she'll be here on Saturday. She went out there like a ton of holes in her schedule. They even closed on Sunday it's always like stressful even just being in there before like it opens because everyone walks around with a mask. And so I'm like like pulling mine up. I'm like so nervous. Putting up his in there.
Like look at this class. Every single day I was more and more students.
Yeah.
It like goes from 3 to 5 absences. I think there's like 6 or 7.
I was just trying to do this asking her was getting all mad that I was like, hold on.
So remember, y, you're going to
Oh.
substitute it with the force, because that's the y. So you're always going to start with y equals mx plus b. Y is your force, m is your slope, so this. X is your stretch distance. You can write it out as stretch distance for now, and then your y-intercept, which so it'll be times stretch distance. Yeah, and that's what you're gonna write. So we're gonna talk about that once everyone puts their answers out. Yeah. So what I want you to do is get it as close to the dots as possible. You might start a little bit above, but it shouldn't hit that because that's kind of an outlier. Exactly. So once you draw your line, I want you to choose points on the line, not necessarily points.
Could it be like beginning to end?
Yeah.
Okay.
All right. Did you guys get an equation? Vincent, Colin, equation, please. Or sorry, Chase. Oh, you did. Thank you.
Yeah.
Yes. That's okay. Well, if you guys got his look at right up there. Perfect. Did you guys get a picture yet?
I did well. Where did we drop the line?
Not always. Some students have minor steps, some students don't.
No, I was playing with
Okay.
Drop bars.
I'll be right with you, Vincent. Times 100.
No, times 100, yeah, so 30.
You're gonna keep it. That's fine.
So it's smaller than the other, right?
So, and it's less, so yours was,
It's called selfish machine.
you get 30. You get 30, so it's 0.3 times 100,
Yeah.
it's 30.
Yeah.
So 30.
And then, so it's this. This is what
Yeah.
So we drop it.
So if whatever you calculate here, if that's less than 5%, yours is 30. So it's not less than 5%.
No, 30 is the slope.
Oh, sorry.
Yeah.
So what's
So our slope is
1.1?
1.2.
Well,
I mean, not slope, I mean, our intercept's 1.2.
okay, so what is the 1.2 divided by your 3
4.
by 4? What's
Right.
that value? Times 100 is
Yeah,
30.
That's what I'm saying. So we drop it.
So no, because 30 is a percent. 30% is 5%.
Oh, so you're saying it's as a percentage. I thought it was just as a value, not as a.
As a percent. So you're gonna keep it, and that's okay. I'm gonna talk about why some have that y-intercept and why some don't.
Those sensors are really bad at small amounts.
That could be it
We
too.
weren't touching it. It's going like between 0 and 7 right now.
Oh, I
And
know.
our numbers are in 0 and 5, so.
Yeah, I know.
Scary reason.
Okay, I still need a red, a yellow, and an orange. You guys are my red. You are my yellow. So whenever you're do I have an orange? Can anyone do the orange spray? Oh, I don't have an orange spray. What am I thinking?
Why me?
Who got the 5X?
You guys are
Did you convert it correctly? Oh wait. Oh no.
Yeah, you're like.
Let me see your. Yeah, because
Yeah.
your. No, not necessarily. So, this should be 5. Did you have your? Oh. We're going to talk about the white. Except for now, okay, so yellow is 35.
That was nothing like light. It was just.
Let me have you clean up your materials and back to your seats, please.
They were like sitting directly on the They were like smoking for an hour. Like I was getting
There's like 7
That's what I'm saying. You were getting
No, phone away. Everyone in their seats. Let's do the analysis. We got different values. Group number 4. I was working through this equation with Alec, and I really think that your force sensor was just way off because the forces should be bigger than decimals. So I think I'm going to drop this one. We can call that a technological error because the force sensor is giving you problems. But I want to compare the rest of these. What's nice is that we actually have another data point for white. We have a slope for each of these. Purple represents the yellow, white represents the black, and we're trying to figure out what the slope represents. So I'm going to grab the smallest slope, which is red. Who has a red? And the biggest slope, which is the green. Who has a green? Okay. So for this and for this analysis, I'm going to have Sam do this. Sam. All right. So Sam is going to take the red spring and the green spring, and I want you to compare them. Tell us which one has more or less stretch, and then we're going to analyze what the slope means for these springs.
The red one is more stretch.
More stretch. Stretch here. And then the green one is going to be stiffer. So that means the higher the slope, or the higher your spring constant, that is the stiffer or the harder your spring is to stretch. So, thank you. So let's give Sam a round of applause. All right. So this is what I want you to put for question number 4. Your spring constant. Spring constant is a new vocabulary word that represents the stiffness, the tightness, how hard it is to stretch your string. That is your slope. And the bigger that number, the tougher your spring is going to be to stretch, right? So we're represented with the variable K. And the units, so here's something that I really want to emphasize to you, is that anytime you write a mathematical model, you need to make sure that instead of y, we plug in what? Instead of my y here, what's my y value in my graph? Say, force. And instead of x, what's my value here? I call it delta x, but it's your spring stretch, right? Spring stretch is a distance, a change in distance. So really, your mathematical model should be force, I'm just going to do blue, is equal to 30 times your delta x plus your y-intercept. The only problem is we also have to include units. So what unit would my slope give me?
Newtons over.
Newtons per meter. Because it is a rise of force and a run of distance. And then my y-intercept, the y is a force, so that has to be in newtons. If I asked you to write a mathematical model on a quiz or a test, you would lose points for not putting the x and the y appropriate variables and for not putting the units for the slope and the y-intercept. So make sure you include that in your mathematical model. So the newtons over meters is part of the slope. The delta x is your x variable. Yeah. Okay, so now we've got the spring constant. The spring constant has a unit of newtons per meter. And let's go ahead and analyze graphically what our springs represent. So before we move on, I'm going to have you, for now, I'm going to skip the LOL chart. But what I want you to do is pull out your post-lab analysis, and we're going to go through all of the equations that you can get out of our lab today. Go ahead and skip the LOL charts for now. We'll do that at the end of class if we have time. But your spring energy lab. First of all, I just included two, but we've already established that the slope represents the spring constant. The difficulty of stretch, how hard it is to stretch it, represents your spring constant. And the smaller the slope, it's easier. The harder the slope, the higher the slope, it's harder to stretch. So we already know all of this stuff. What I want you to write down is the general mathematical model for any spring. These are the different mathematical models for the different springs we used in class. But for a general mathematical model, you would have the force of the spring equals negative K times delta X. Spring constant times your spring stretch. You're going to write it so you know how it has the bottom half. This is the bottom half right here. Under equations, you can write down this equation. So Hooke was the one who came up with this relationship, so they called this relationship Hooke's law. But why is it negative when you guys had a positive value? Any thoughts? Ellen? So if you think about it, if I pull the spring to the right, what direction is the force of the spring pointing in? To the left. It opposes the applied force. It also opposes the direction you are stretching in, right? So if I'm stretching it to the right, my force is going to point in the opposite direction, and vice versa. If I pull my spring to the left, then the force of the spring is pulling me to the right. That's why there's a negative there. So why is it a negative? Because it opposes the direction of stretch. This is an equation in your physics helper. The other thing we want to write down is that the slope, we already talked about this, represents the spring constant. But what does the area under the curve represent? So this I'm going to have you write in your graph. I want you to think about this. As you stretch your spring a little bit bigger and bigger and bigger, the area under the curve gets bigger and bigger and bigger. Not a direct relationship, but more like a exponential relationship. But what is some characteristic of a spring that as I stretch it, that characteristic increases, that value, that quantity. Elastic potential energy. My students last class said force, but we already have force represented here. The more I stretch it, the more elastic potential energy is stored in my spring. So area under the curve represents elastic potential energy, E sub EL. You can also call it EPE. Okay, so we're going to figure out what these equations are. These equations are already in your physics helper. And sure, I could give them to you and you can calculate with them, but they actually come from the graph that we created in this lab today. So first of all, the area under the curve is 1/2 base times height. The base represents my delta x. The force represents my spring force. In your physics helper, they just flip these two around, and this is what you're going to see for one of your elastic potential energy equations. So this goes under equation. Area under the curve and 1/2 force times delta x. 1/2 the force of the spring times the distance the spring stretched. They give you a second equation though. And the reason why they give you a second equation is just in case you don't know what the force is, then you can use this next one. Basically, all they did was they took, another thing, the unit for elastic potential energy is newtons times meters, because force is in newtons, delta x is in meters, but for energy in general, we call that unit J for joules. So this is your unit for energy. Either Newton meters or joules, J. That's a new variable that you're going to have to memorize. Okay, let's go into our second equation. If I took the equation for elastic potential energy, but instead of force, I substituted my K delta X, I'm leaving out the negative. And the reason why is because energy, force is always going to be opposite, but energy not necessarily. So we're just going to think about it as the absolute value or the magnitude. But if I substitute this in here, and I simplify that, this gives me my second elastic potential energy equation, 1/2 K, which is your spring constant, times delta x squared. And again, your unit is newtons per meter, and your unit can also be represented by J for joules. So you have 3 new equations, 1 for spring force, 2 for elastic potential energy, and you also have 2 graphical analysis concepts. One is the fact that the spring constant is your slope, and 2 is the fact that the area under the curve is your energy. So this is my recap. Equations are here, and graphical analysis is here.